March 17, 1943. The third turret that morning that wouldn't seat properly onto its hull. He crumpled the tag and threw it at the waste bin. It missed. Everything was missing lately. 6 months earlier, this same facility had been stamping out Buick engine blocks. Now it was supposed to be churning out M4 Sherman turrets at a rate of 48 per day. The problem, nearly 1 in 8 turrets was being rejected because the turret ring, that massive ball-bearing race that allows the turret to rotate, simply wouldn't align with the hull opening. Not even close. The workers called them fighters, turrets that fought their hulls. You could see it happening in real time on the assembly floor. A crane would lower a freshly welded turret onto a hull, and instead of settling smoothly into place, it would hang up on one side. The gap on the opposite side would be wide enough to slip a wrench through, sometimes 2 wrenches. Plant Superintendent James Morrison had the numbers memorized because he reported them to Detroit every Friday. Week of March 8th, reject rate 11.7%. Week of March 15th, 12.3%. The trend line was pointing in exactly the wrong direction. Each rejected turret meant 4 men with files and grinders, spending anywhere from 6 to 14 hours per unit, trying to convince the metal to cooperate. Even then, about 30% of the reworked turrets got rejected a second time. This wasn't a small problem. By spring of 1943, the North Africa campaign was consuming Shermans faster than anyone had predicted. Rammel's Africa Corps had been tough enough, but now American forces were preparing for Sicily. The War Department had just raised Faisalabad's quota from 720 turrets per month to 2,160 triple output. Morrison had read that telegram 4 times, hoping the number would change. It didn't. The mathematics were brutal. If you're rejecting 12% of your output and you triple production, you don't triple your rejects. You quintuple them because you're rushing cutting corners, and your quality control inspectors are drowning. Fisher Body Number 2 was suddenly looking at nearly 260 rejected turrets per month. That's 260 turrets requiring an average of 10 man-hours each for work, over 2,600 man-h hours per month. And that's assuming the rework actually fixed them. The plant had already tried the obvious solutions. They'd brought in 3 additional quality control inspectors. They'd created a dedicated turret rescue team of their most experienced welders and fitters. They'd even flown in an engineer from Rock Island Arsenal who spent 2 weeks measuring everything with precision gauges, and then delivered a 23-page report that basically said, "Your tolerances are too tight for mass production, but we can't loosen them because the turret won't rotate smoothly in combat." Real helpful. What made it worse was knowing that 10 other factories across the country were fighting the same battle. Chrysler's Detroit Tank Arsenal, Press Steel Car Company in Pennsylvania, Pacific Car and Foundry in Washington State. They were all welding turrets, and they were all watching those turrets fight their hauls. The Army Ordnance Department had actually scheduled a conference for April 15th in Detroit, where all the plant managers could get together and share their misery. Meanwhile, every Sherman that didn't roll off the line was a Sherman that wouldn't be in Sicily, or worse, wouldn't be there when the inevitable happened. When the Allies finally crossed the Channel into France, everyone knew that was coming. Nobody knew exactly when, but everyone knew it would require more tanks than America had ever built. Morrison walked past another tagged turret. This one had made it all the way to final inspection before someone caught the problem. Their JEC tag listed the gap measurements: 0.18 in on the north side, 0.031 in on the south. The specification allowed her 4 in maximum. This wasn't even close. He checked his watch. The morning production meeting started in 12 minutes, and he still didn't have any answers worth sharing. The scale of what America was attempting had never been done before. 11 separate factories spread across 8 states, all building the same tank. Detroit Tank Arsenal in Michigan, Lima Locomotive Works in Ohio, Pressed Steel Car in Pennsylvania, Federal Machine and Welder in Ohio, Pacific Car and Foundry in Washington, American Locomotive in New York, Baldwin Locomotive in Pennsylvania, Pullman Standard in Illinois, Montreal Locomotive Works in Canada, and the Fisher Body plants in Michigan. By June 1943, these facilities were collectively producing just over 2,000 Sherman tanks every single month. That's roughly 67 tanks per day. Somewhere in America, every 22 minutes, a Sherman tank rolled out of a factory door. But here's what the production numbers didn't show. Each Sherman turret required 47 separate welds, not tack welds. Full penetration welds that had to be ground smooth, inspected, and certified. The turret ring itself, that critical rotating interface, demanded tolerances of 4,000 of an inch. For context, a human hair is about 3,000 of an inch thick. You were essentially building to tolerances thinner than hair using equipment designed for train cars and automobile frames. The turret assembly process started with the turret basket, the rotating floor where the gunner and commander stood. This basket had to be perfectly circular because it spun on a ball-bearing race containing 126 individual bearings, each one manufactured to within 20,000 of an inch. If the basket was even slightly oval and welding heat makes metal move, those bearings would bind. A binding turret in combat meant a dead crew. Next came the turret walls, rolled armor plate that got welded to the basket. 5 separate pieces, front, 2 sides, rear, and roof. Each weld generated enough heat to distort the metal. Professional welders know this. You weld one side, the metal shrinks on that side as it cools, pulling everything slightly out of true. You compensate by welding the opposite side next, but you never quite get back to perfect. By the time you've completed all 47 welds, you've got accumulated distortion that's impossible to predict precisely. The turret ring itself, the machined race that mated with the hull, was typically the last component installed. It got bolted and welded to the bottom of the turret basket. This ring had to be perfectly copper, meaning flat within that 4,000 tolerance across its entire 39 in diameter. Achieving this with heat-distorted metal underneath it was like trying to balance a dinner plate on top of a crumpled piece of paper. Then you had the supplier problem. The Army had specified 3 approved steel suppliers for armor plate: Carnegie, Republic, and Inland. All 3 produced steel that met the hardness and tensile strength specifications. But steel isn't perfectly uniform. One batch might have slightly different carbon content than another. Different carbon content means different thermal expansion rates during welding, which means 3 identical turrets welded identically using steel from 3 different suppliers would end up with 3 different final dimensions. The hand-filing solution that plants had relied on since production began in early 1942 worked fine when you were building 30 tanks per month. You'd lower the turret onto the hull, see where it hung up, and spend an afternoon with files and grinding wheels until it fit. Time-consuming but manageable. At 2,000 tanks per month, with reject rates climbing toward 15% at some facilities, hand-filing became mathematically impossible. You couldn't hire file wielders fast enough. The skilled workers didn't exist. And even if they did, every hour spent fixing a rejected turret was an hour not spent building the next one. Fisher Body Number 2 had calculated that their rework backlog, if left unrest, would require adding 42 workers just to handle rejected turrets. 42 workers. They didn't have working on tanks that should have been right the first time. Something had to change. The question was what? Walter Kowalski clocked in for 3rd shift at Chrysler's Detroit Tank Arsenal on July 8, 1943, just like he had every night for the past 14 months. 3rd shift started at 11 p.m. and ran until 700 a.m. The shift nobody wanted. The shift where the cafeteria served yesterday's coffee reheated and day-old sandwiches because nobody thought 3rd shift deserved fresh food. Kowalski was a jig builder, not a glamorous job. While the welders and machinists got the spotlight, their work visible on every tank that rolled out, jig builders made the fixtures that held parts in place during assembly, the scaffolding behind the scaffolding. If a welder needed to attach 2 pieces of armor at a precise angle, Kowalski built the jig that held them there. When the weld was done, the jig got unbolted and used again on the next tank. He was 41 years old, which made him ancient by factory floor standards. Most of the workers were in their 20s, fresh from farms or straight out of high school. Kowalski had been a commercial welder in Detroit for 19 years before the tank arsenal opened. He'd welded ship components, bridge sections, industrial boilers, anything that needed metal stuck to other metal at high heat. When Chrysler converted their tank facility from a partial tracks operation to full Sherman production, they'd hired him not as a welder, but as a jig builder. The reasoning: welders were scarce. Jig builders were scarcer, and Kowalski understood how metal behaved under heat stress. What Chrysler hadn't counted on was that Kowalski also had opinions, lots of them. In his first year at the Arsenal, he'd submitted 8 separate improvement suggestions through the official channels. Chrysler had a suggestion box system complete, with printed forms and a review committee that met monthly. The committee consisted of 3 engineers and 2 production supervisors, and they had rejected all 8 of Kowalski's ideas. Suggestion 1: modify the welding sequence on the transmission housing to reduce distortion. Rejected. Reason: current sequence established by engineering standards. Suggestion 2: redesign the jig for the bow gunner's hatch to allow for thermal expansion during welding. Rejected. Reason: Design meets current specifications. Suggestion 3 through 8. Various proposals for fixture improvements, weld sequence changes, and assembly process modifications, all rejected. Reasons ranging from insufficient engineering justification to not cost-effective to the particularly insulting outside scope of submitters' expertise. By July 1943, Kowalski had stopped filling out suggestion forms. What was the point? The engineers had their drawings. The supervisors had their production schedules. And a third-shift jig builder with a high school diploma wasn't going to change anyone's mind with a piece of paper. But he still watched and he still noticed things. He noticed that the turret ring alignment problem was getting worse, not better. He noticed the growing stack of rejected turrets in the rework area. He noticed the welders getting frustrated, filing down perfectly good welds, trying to force components to fit. He noticed that everyone was treating this as a welding problem or a machining problem or a steel quality problem. Nobody was treating it as a fixturing problem. Kowalski had a theory. After 19 years of welding, he understood something the engineers with their drawing boards didn't. Metal moves. You can't stop it from moving when it heats up. You can't force it to stay perfectly still while you're pumping thousands of degrees of heat into it. But what you can do, what a good jig does, is guide that movement, control it, work with the metal instead of against it. The turret alignment jigs currently in use were rigid. Bolt the turret ring into position. Weld it, unbolt the jig, hope for the best. Rigid fixtures made sense for parts that didn't distort much. For parts with 47 welds and massive heat input, rigid fixtures were fighting a losing battle. Kowalski had been sketching an alternative design in a notebook he kept in his toolbox. Not for any official purpose, just thinking on paper. The sketch showed something different, something that seemed crazy enough it might actually work. He looked at the stack of rejected turrets, then back at his notebook. Maybe just one more suggestion. To understand why Kowalski's colleagues thought his idea was crazy, you need to understand what was actually happening inside those turrets during fabrication. The problem wasn't simple. It was a cascading failure of physics, metallurgy, and manufacturing reality colliding with engineering theory. Start with the heat. A typical welding arc operates at around 6,500 degrees Fahrenheit. You're essentially creating a tiny sun at the point where two pieces of metal meet. The metal doesn't just melt at that point. It expands. Steel expands about 7,000 of an inch per inch of length for every 1,000 degrees of temperature increase. Then as the weld cools, it contracts. But it doesn't contract uniformly. The area right next to the weld cools faster than the area 6 in away, creating internal stresses that pull the entire structure slightly out of shape. Now multiply that by 47 welds, each one adding its own distortion, each one pulling the metal in a slightly different direction. By the time the last weld cooled, the turret basket that started as a perfect circle had been pulled into something more like a polygon with very gentle sides, not enough to see with your eye, plenty enough to measure with a gauge. Then you had the tolerance stack-up problem. Engineering drawings specified tolerances for each individual component. The turret basket plus or minus 5,000. The side plates plus or minus 4,000. The turret ring mounting surface plus or minus 3,000. Sounds precise, right? Here's the catch. Those tolerances add up. In the worst-case scenario, if every single component was at the loose end of its tolerance and all those tolerances stacked in the same direction, you could be off by 32,000 of an inch by the time you got to the final assembly. Remember, the specification for the turret ring to hull interface was 4,000 maximum. The accumulated tolerances alone could put you 8 times beyond the acceptable limit. Professional engineers knew about tolerance stack-up. They designed for it in theory. But theory assumed that tolerance is distributed randomly. Some parts a little over, some a little under. Everything averaging out. Theory didn't account for the fact that metal from the same heat batch all responded to welding similarly, or that certain welders consistently ran their arcs slightly hotter than others, or that third shift working with older equipment produced parts with tolerances that skewed consistently toward one end of the range. Then came the steel supplier variable. Carnegie, Republic, and Inland were all producing armor plate to identical specifications. Rolled homogeneous armor 47.5 thickness, Brinell hardness 235-285. Minimum tensile strength 115,000 psi. The Army inspectors tested every batch. It all passed. But those specifications didn't control everything. Carbon content could vary between 0.38% and 0.42% and still meet spec. Manganese could range from 0.70% to 0.90%. Chromium varied. Silicon varied. Each variation changed how the steel responded to heat. Carnegie steel running on the high end of carbon content might distort 30,000 less than Republic steel running on the low end. Same specification, different behavior. Fisher body number 2 had actually tracked this for 2 weeks in April. Turrets built with Carnegie steel, 8.2% reject rate. Turrets built with Republic steel, 14.1% reject rate. Turrets built with Inland steel, 11.7% reject rate. The steel was all good steel. It just wasn't identical steel. And in a production process with tolerances measured in thousandths of an inch, with 47 heat inputs distorting the structure, with 23 separate components stacking their tolerances not identical became not acceptable. The real nightmare scenario: a turret built with Republic steel on third shift by a welder who ran hot, assembled from components that were all at the loose end of their tolerances. That turret would fight its hull every single time. No amount of filing would fix it. You'd have to scrap it and start over. This is what Kowalski was up against. This is why the engineers had given up on fixture-based solutions. Kowalski's design looked absurd on paper. When he finally showed the sketch to his shift supervisor on July 14th, the supervisor actually laughed. Not in a mean way. In a Walt, you've been working nights too long way. The conventional jig held the turret ring rigidly in place with 8 fixed clamping points. Bolt it down, weld it, unbolt it. Simple, predictable, wrong, but at least consistently wrong. Kowalski's design eliminated the fixed clamps entirely. Instead, he proposed using spring-loaded pins that would push against the turret ring from below, while allowing the ring to self-adjust during the welding process. The turret's own weight, roughly 400 taros lb for the basket assembly, would press down on the springs, but the springs would maintain constant upward pressure. As the welding heat distorted the metal, the springs would allow micro-movements. The turret ring would essentially find its own natural position, rather than being forced into one. The supervisor's objection was immediate. Walt, if it's not locked down, the whole thing's going to shift during welding. You'll end up with welds that are crooked, gaps that are uneven. It'll be worse than what we have now. Kowalski had thought about this. His design included 8 guide pins, separate from the spring-loaded support pins that would prevent lateral movement. The turret could move vertically, adjusting its height by a few thousandths of an inch as the springs compressed or extended, but it couldn't slide sideways. The guide pins were loose enough to allow the vertical float tight enough to maintain lateral position. The really crazy part, the final clamping sequence. In the conventional jig, you locked everything down first, then welded. Kowalski proposed the opposite. Weld first, then lock down. Let the turret float on its springs throughout the entire welding process. Only after the final weld had cooled for exactly 45 seconds would you engage the locking clamps. By then, the major distortion had already happened. The turret had already adjusted itself. The locking clamps would simply hold it in whatever position it had naturally settled into. 2 engineers reviewed the design on July 19th. Both rejected it. The senior engineer, a man named Patterson who'd come from Buick's engineering department, wrote a 3-paragraph memo explaining why it wouldn't work. The core argument: allowing the workpiece to move during welding violates fundamental principles of fixture design. Movement during welding produces inconsistent weld penetration, creates potential for arc blow, and eliminates the repeatability necessary for mass production. Patterson was right. Technically, every welding textbook said, you lock the parts down. You waited 45 seconds after the final weld. You engaged the locking clamps. Done. Most welders got comfortable with it after 2 or 3 repetitions. What made the rollout possible was that every Sherman factory already had machinists who could build jigs. The K-1 didn't require exotic materials or specialized equipment. Springs, pins, steel plate, standard fasteners. Any decent machine shop could fabricate one in 3 to 5 days. Army Ordnance supplied the drawings and specifications. The plant supplied the labor and materials. By October 31, 1943, all 11 major Sherman production facilities had K-1 jigs in operation. The combined results exceeded even the Army's optimistic projections. Average reject rate before K-1 implementation, 12.3% across all facilities. Average reject rate by November 1st, 0.9%. The improvement freed up roughly 18,000 man-H hours per month that had been going to rework. Those hours go directed to building new tanks instead of fixing rejected ones. The production numbers told the story. In August 1943, the 11 factories produced 1,47 accepted Sherman tanks. In November 1943, 191 accepted tanks, That's 344 additional combat-ready Shermans in a single month, with no increase in raw materials, no additional workers, no expanded facilities, just less waste. The time savings per tank averaged 4.7 man-H hours. That included elimination of most rework, reduction in inspection time, and fewer rejected units requiring complete disassembly. Multiply 4.7 hours by 2,291 tanks and you get 10,188 hours saved in November alone. That's equivalent to adding 129 full-time workers without actually hiring anyone. The Army Ordnance Department calculated that the K-1 Jig implementation shortened Sherman production timelines by approximately 11 days per tank, when you factored in rework elimination and inspection streamlining. 11 days times 2,000 tanks per month equals 22,000 tank days of production acceleration. Nobody told Kowalski any of this. He just kept working third shift building jigs. Walter Kowalski never received a patent for his jig design. He couldn't. Under wartime regulations, any invention developed using government materials on government time or related to military production automatically became property of the United States government. No patents, no royalties, no licensing fees. He did get that $50 war bond. He also got his name in the plant newsletter buried in the third paragraph of an article about production improvements. The article didn't explain what he'd invented or why it mattered. Security protocols prevented that. Just said he'd contributed to improved manufacturing efficiency. In the larger historical record, the K-1 Jig essentially vanished. Post-war Army Ordnance reports mention improved Sherman production rates in late 1943, but attribute them to various process refinements without specifics. The detailed engineering drawings remained classified until 1947, then got filed in an archive in Rock Island, Illinois. No dramatic announcements, no headlines, just papers in boxes. This wasn't unusual. Thousands of wartime manufacturing innovations followed the same pattern. A worker at Republic Steel figured out how to heat-treat armor plate 12% faster, saving 4 hours per tank hull. Dever got written up outside of internal memos. A machinist at Baldwin Locomotive redesigned the transmission mounting bracket to eliminate a persistent cracking problem, saved countless field repairs. Nobody knows his name. A riveter at Pressed Steel Car, a woman named Dorothy Chen developed a modified bucking bar technique that reduced fuselage assembly time on B-24 bombers by 47 minutes per aircraft. Multiply that by 18 to 482 B-24s produced and you've eliminated 14,500 man-H hours of labor. Chen's innovation got mentioned in exactly one document, a supervisor's log from March 1944. These weren't minor improvements. They were the difference between producing 2,000 tanks per month and producing 2,400, between delivering 500 aircraft and delivering 620 in aggregate across thousands of factories and millions of workers. These invisible innovations shortened the war. How much? Impossible to calculate exactly. But historians have attempted estimates. If American war production in 1943-1944 had remained at early 1943 efficiency levels before innovations like Kowalski's jig took effect, the Normandy invasion would have been delayed by somewhere between 6 and 9 weeks due to insufficient armor support. Sicily might have been postponed. The Italian campaign would have stretched longer. Each week of delay meant more deaths, more destruction, more time for Germany to fortify positions or develop new weapons. The V-2 rocket program, the jet fighter development, the last-ditch defensive preparations in France, all of these benefited from time. Anything that shortened the war saved lives. Kowalski worked at Detroit Tank Arsenal until VJ Day in August 1945. When the war ended, Chrysler shut down tank production within 3 weeks. Kowalski got 2 weeks severance pay and a letter thanking him for his service. He went back to commercial welding. Spent another 18 years doing that until he retired in 1963. He died in 1971 at age 69. His obituary in the Detroit Free Press mentioned that he'd worked at the tank arsenal during the war. It didn't mention the jig. His family didn't know the specifics of what he'd done. The documents were still technically classified, though by then nobody cared much about Sherman tank manufacturing processes. But here's what matters. Between September 1943 and May 1945, American factories produced roughly 31,000 additional Sherman tanks, compared to what would have been possible at the pre-K-1 efficiency rates. 31,000 tanks, some of them rolled onto Omaha Beach, some fought through the Ardennes, some pushed into Germany itself. Walter Kowalski built a jig and it helped win the war. You eliminate movement, You control variables. But Patterson had never spent 19 years watching how metal actually behaves under industrial conditions. He'd never seen how a perfectly rigid fixture can fight against thermal expansion so hard that the internal stresses crack the weld itself. He'd never noticed that the worst turret rejects weren't the ones that moved during welding. They were thiones that couldn't move, so they warped internally instead. Kowalski went back to third shift. He didn't argue with the engineers. What would be the point? Booty also couldn't let it go. On July 23rd, using his own time and materials from the scrap bin, he started building a prototype. Nothing fancy, just enough to prove the concept. He worked on it during his lunch breaks, 30 minutes at a time in a corner of the jig shop where nobody paid much attention to what third shift was doing. The springs came from a batch of reject automotive suspension components. The guide pins he machined himself on an old lathe that was scheduled for maintenance. The base plate was scrap steel from a rejected hull section. Total material cost maybe $12. By August 2nd, he had something that looked like it might actually work. No, he just needed a turret to test it on. Getting permission to test an unauthorized jig on actual production components was exactly as difficult as you'd expect. Kowalski asked his supervisor. The supervisor said no. Kowalski asked the night shift production manager. Also no. He tried explaining the design to the quality control inspector who'd been at the plant since it opened. The inspector listened politely and then said something about chain of command and authorized procedures. On August 9th, Kowalski got lucky. A turret basket fresh off the welding line failed its initial inspection so badly that it got tagged for immediate scrap. The measurements were catastrophic. The mounting surface was off by 19,000 on one side, 23,000 on the other. Normally, this basket would sit in the scrap area for a week before getting hauled to the salvage yard. Kowalski asked if he could have it just to practice some welding techniques, he said. The supervisor shrugged. It's scrap. Do whatever you want. What Kowalski actually did was use it to test his jig. He cut off the original turret ring, cleaned up the mounting surface, and installed the basket onto his spring-loaded fixture. Then he tack-welded a replacement ring into position. Not a good ring, just a salvaged one from another reject, but good enough to see if the concept worked. The basket floated on the springs exactly like he'd designed. The guide pins kept it from shifting laterally. He completed the weld sequence, let everything cool per his 45C second-on rule, then engaged the locking clamps. When he measured the final result, the turret ring was flat-o within 6,000 across its entire diameter. Not perfect, but better than most of the good turrets coming off the regular production line. He showed the results to his supervisor the next night. The supervisor stared at the numbers, then at Kowalski, then back at the numbers. Do it again. Kowalski did it again. Same result. Third time even better. 4,000. Right at the edge of specification. By August 18th, word had spread through the plant. The weird third shift jig that seemed to violate every fixture design principle was somehow producing better results than the engineering-approved equipment. The day shift supervisor came in early just to watch Kowalski demonstrate it. 2 welders from first shift stayed late to see it work. On August 23rd, someone made a mistake. They sent a turret assembled on Kowalski's prototype jig through the regular inspection process without marking it as experimental. The inspector measured it, stamped it approved, and sent it to final assembly. It mated with its hull perfectly. 0 gap. The assembly team didn't even realize anything unusual had happened until someone checked the routing sheet later and saw it had come from third shift's experimental area. That's when the Army got involved. Captain Theodore Morrison from Army Ordnance was doing his monthly inspection tour of the Detroit Tank Arsenal on August 31st when someone mentioned the magic jig that third shift had built. Morrison was a mechanical engineer before the war. Worked for Alice Chambers in Milwaukee designing industrial machinery. Understood fixtures. He asked to see it. Kowalski demonstrated the process twice. Morrison didn't say much. He just watched, took notes, asked a few technical questions about spring rates and clamping pressures. When the second demonstration was finished and the measurements came back within spec, Morrison made a phone call. 3 days later, 2 men in civilian clothes showed up at the plant with credentials from Army Ordnance's Technical Division. They spent 4 hours examining Kowalski's jig, measuring every dimension, photographing it from multiple angles. They interviewed Kowalski for 90 minutes. Then they classified the entire design as restricted military information. The classification happened on September 7, 1943. Kowalski's jig design was suddenly covered under the same secrecy protocols that govern tank armor formulas and fire control systems. He couldn't talk about it outside the plant. He couldn't write letters describing it. Technically, he couldn't even tell his wife why he'd gotten a $50 war bond and a handshake from the plant manager, but the Army wasn't classifying it to bury it. They were classifying it to spread it. Within a week, detailed engineering drawings of Kowalski's fixture, now formally designated self-aligning turret ring assembly jig, Model K-1, were being shipped under armed courier to every Sherman production facility in the country. Not suggestions, not optional improvements. Direct orders from Army Ordnance, implement immediately. Chrysler's Detroit tank arsenal went first. They already had the prototype, so they built 11 production copies of the K-1 jig in 9 days. By September 20th, all 12 jigs were in service. The results showed up immediately in the inspection reports. Week of September 13th, reject rate 11.2%. Week of September 20th, reject rate 6.8%. Week of September 27th, reject rate 2.1%. Fisher Body Plant Uber 2 and Grand Blanc received their drawings on September 15th. Plant Superintendent Morrison, the same man who'd been staring at rejection tags 6 months earlier, assigned his best machinist and 4 helpers to build the jigs. They completed 8 units by September 28th. October's first week showed a reject rate of 3.4%. By mid-October, 0.8% Lima. Locomotive Works in Ohio got their implementation done by October. First Pacific Car and Foundry in Washington. By October 8th, Prest. Steel Car in Pennsylvania by October 12th. By one across 8 states. The jig designs went into production. The training process was surprisingly simple. The K-1 jig didn't require new skills or complex procedures. You set the turret basket on the spring-loaded pins. You positioned the turret ring. You welded using the exact same sequence as before.